Welcome to Chem We Talk, a channel where we are not afraid to talk about any chemistry topic. In today's video, we will discuss how to determine the pH range of solutions containing salts. Let's start the video by looking at these three important questions. What is a salt? What is a salt made of? And how is a salt produced? Salts are simply charge-neutral ionic compounds that are made of positively charged ions and negatively charged ions. The most common method of producing salt is through a reaction called neutralization. In the neutralization reaction, an acid and a base react together to produce salt and water as a byproduct most of the time. We can see that this type of reaction is a double displacement reaction where the cations and the anions get swapped to produce salt and water. We see that the cation from the base, the Na+, reacts with the Cl- from the acid to produce the NaCl salt, and the H+ from the acid reacts with the OH- from the base to produce water as a byproduct. However, knowing the answer to those three questions so far does not respond to the main question of this video, which is how can we predict the pH range of a solution containing a salt? Okay, before digging into the science and reactions necessary to answer the question, let's spend some time talking about dog breeds. And let's use this Bernedoodle as an example. If I were to ask you how to explain some of the observed traits of this doodle, such as the color of its fur or the shape of its nose and ears, what would be the answer? In biology, whenever we want to understand the characteristics of the offspring, we need to look at the characteristics of the parents. In the case of this doodle here, the parents are a poodle and a Bernese mountain, and we can clearly see that the Bernedoodle displays some of the characteristics from the poodle, such as the type of fur, and some of the characteristics from the Bernese mountain, such as the fur color, this black and white pattern. The discussion might sound a little silly and out of context, but we can draw a parallel between the characteristics of this doodle and salts. While one needs to know the parents of the doodle to understand its traits, one needs to understand the characteristics of the acid and the base that form a salt in order to understand if the salt will be acidic, basic, or neutral. Okay, so let's look at this first example here using lithium chloride. The first step is always to break down the salt into its ions. Okay, so in this case, lithium chloride in water will break apart producing lithium plus and Cl minus. The second step is, okay, this is a salt. It comes from an acid and base reaction. What are the base and the acids that produce those two cations, or those two ions, the cation and the anion? Okay, so we know that lithium, the cation from the salt, comes from a base, in this case lithium hydroxide, which is a strong base. If you remember your list, this is lithium is from group 1A, so it's going to be a strong base. And HCl would be the acid that produced the Cl- anion. And if you remember again, this here is one on the list of your 7 strong acids that you should memorize. So we have lithium hydroxide and HCl. Those both come from strong species. At this point, if it comes from a strong base and a strong acid, you should already know that the salt should be neutral. But let's do some more investigation. So lithium hydroxide is a strong base. So in water, we know that it splits into lithium plus and OH minus. And we know that's like a single error reaction, which means that once lithium hydroxide gets in water, it goes all the way to lithium plus and OH minus, and there's no reverse reaction, which means that lithium plus is in fact what's called a spectator ion. It doesn't go into reverse reaction. Same thing happens with HCl. HCl in water would split and produce H plus and Cl minus in a single error reaction, which means that once the H plus is formed, it doesn't react back as well as the Cl minus. So the Cl minus does not react back to to produce HCl, which means it is a spectator ion as well. And we get what's called neutral salt. So if it comes from a strong base and strong acid, your salt will be neutral. Let's look at a similar example, but now instead of having lithium chloride, we have lithium fluoride. So lithium, again, we broke apart. It's got lithium plus and F minus. Once we look at the base that produces lithium, it's going to be lithium hydroxide, which is a strong base. F minus, on the other hand, comes from HF, which is a weak acid. It's one of the exceptions. It's in group 17, but it's the sole exception. It's the first one from group 17. Let's do the same analysis. We put lithium hydroxide in water. We get lithium plus and OH minus, which means it's a single error reaction. So lithium plus does not react back, and it's called a spectator ion. However, HF, when you put it in water, you can note now that I have a double arrow. and we're producing H plus and F minus. And the double arrow seems to mean that some of those products can react back to produce HF, which means that F minus is not a spectator ion anymore. So we have lithium plus being a spectator and F minus being a weak base, or the conjugate base of HF. But if you just look at the parents, like we did for the doodle example, we have lithium hydroxide being a strong base and HF being a weak acid. The strong overcomes the weak, and your salt will be basic. And the reason why is that weak acid will produce a non-negligible conjugate base, which is going to be the F minus. That's what causes the salt to be basic. We're going to discuss a lot about that in a future video when we actually will do calculations, but that's like the reasoning. All right, let's look at a third example where we have NH4 and NO3, or ammonium nitrate. We do always the same thing. We break into its ions, so we have the NH4 cation and we have the NO3 minus anion. Where does NH4 plus come from? It comes from ammonium, which is a weak base. Remember, your strong bases are only group 1A and 2A, with the exception of beryllium and magnesium, which are weak bases because they're not very soluble. And we have NO3 minus coming from HNO3, which is one of the strong acids that you should memorize. Okay, so just by looking here, it comes from a weak base and a strong acid. We know strong acid versus weak base. The strong should win, and that should be an acidic salt. But let's all do the analysis again. So NH3, which is a weak base, if you put in water, it has a double arrow reaction, producing NH4 plus and OH minus, which means again that this NH4 plus can go back and react, which means this NH4 plus will not be a spectator. On the other hand, if you look at HNO3, when you put that in water, it breaks apart to H plus and O3 into a single arrow reaction, which means that NO3 minus cannot come back and produce HNO3 again, and that is a spectator ion. Okay, and we're going to have an acidic salt because we have the presence of this NH4 plus weak conjugate acid of ammonium. But again, just by looking at the parents here, you saw this was coming from a weak base and a strong acid. The strong wins, and you have this acidic salt. All right, let's look at our last example. Now we have ammonium fluoride. So we did the same exact thing. We broke into its ions. Let's look at the parents of those ions. We can see that the parent of NH4 plus was NH3, and the parent of F minus was HF. NH3 is a weak base, while HF is a weak acid. So now we might have a problem. Would this here means it's going to be a neutral like we have when we had a strong and strong? Let's look at the reactions individually. So we have NH3 plus H2O in a double arrow reaction producing NH4 plus and OH minus. And we have HF, which is a weak acid, producing H plus and F minus. So in both cases, NH4 plus can go back to produce NH3, and F minus can go back to produce HF. So none of those are spectators. We have NH4 plus being the conjugate acid of NH3, and we have F minus being the conjugate base of HF. So how do you determine which one's going to be stronger, the NH4 plus or F minus? So what we need to do is, in fact, it's a little bit more complicated than the other cases, but we need to look at the Ka and the Kb of the conjugates, or the ions in solution. And we can see that the Ka of NH4 plus is 5.6 times 10 to the negative 10, while the Kb of F minus is 1.5 times 10 to the negative 11. Those are both very small numbers, but the Ka of NH4 plus is still larger than the Kb of F minus, which means that this salt NH4F would in fact be acidic. All right, so now that we understand a little bit more how to predict the pH, let's put that in perspective here. Let's do an example or a practice problem. Let's start with calcium acetate. Okay, so calcium acetate, this very complicated formula here. Sometimes when I have a conjugate base like acetate, formate, benzoate, I don't remember the formula from organic chemistry, I just represent this whole thing as A minus and call it a day, so CaA2, but the formula for acetic acid or acetate is CH3COO. Okay, so let's do the same process. Let's look at the base and the acid that produce this salt. So CaA2 produces calcium 2 plus and 2A minus or acetate ions, and the calcium 2 plus comes from calcium hydroxide, which is a strong base, and the A minus comes from HA or acetic acid, which is a weak acid. Okay, so if it comes from a strong base and a weak acid, we're going to get a basic salt. So the strong overcomes the weak. Very simple. Let's look at the next example. We have rubidium bromide, RPBr. Let's put in water, break into its ions, so we have rubidium plus and Br minus. Rubidium plus comes from rubidium hydroxide, which is a strong base, and then Br minus comes from HBr, which is a strong acid. So if a species comes from a strong base and a strong acid, we're going to get a neutral salt. None of those are going to overcome each other. Okay. Let's look at the next one, CH3 and H3Cl, or methyl ammonium chloride. Let's do always the same thing. Put those ions, put the compound in solution, break into its ions, and see what were the parents. So CH3 and H3 plus comes from this methylamine, CH3 and H2, which is a weak base, it's not on the list that you memorize. And then we have Cl minus that comes from HCl, which is probably the most famous strong acid. So when you compare those two, you have a weak base and a strong acid. The strong overcomes the weak, and you're going to get an acidic salt. Next example, we have ammonium bisulfate, NH4HSO4. And let's look at the ions again. So we have NH4 plus and HSO4 minus. NH4 plus comes from NH3, which is a weak base, while HSO4 minus comes from H2SO4, which is one of the strong acids, and it's the only diprotic strong acid that we memorize. So when we compare here, we have weak base and strong acid, we're going to get an acidic salt, so following the same thing. Now I'm going to just warn you that the next case is going to be a little bit tricky, but let's do it step by step. So sodium bisulfate, now we have sodium HSO4, which is going to produce Na plus and HSO4 minus ions in solution. The Na plus comes from an NaOH, very popular strong base. HSO4 minus comes from H2SO4, which is a strong acid. And one would naively think that if this comes from strong base and strong acid, that would be neutral, right? But there's a problem. The Na plus, which comes from a strong acid, from a strong base, it is in fact a spectator ion. But the problem is HSO4 minus, which is an anion coming from a strong acid, because H2SO4 is diprotic, it still has an extra hydrogen to be removed. So this here, it's not, and the spectator ion itself is in fact a very strong weak acid. So it can lose another hydrogen, and if you look at the Ka of it, HSO4 is 1.2 times the -2, which is pretty large. So this salt is in fact acidic. But that's one of the sole exception you need to pay attention when you have like a diprotic species. Okay, so moving on to the last example, we have ammonium acetate. So this one is actually another tricky example. But let's go slowly. So we have NH4, CH3COO. We put in solution, we get NH4 plus and CH3COO minus. We do the same process. We get NH3, or originating NH4 plus, which is a weak base. And we have H3COOH, which is acidic acid, which is also a weak acid. So if you come from a weak base and a weak acid, we need to look at the Kas and Kbs, right? But this is a funny coincidence because the Ka of acidic acid and the Kb of ammonia are exactly the same. So it turns out that you get a neutral salt, but it only is neutral because Ka and Kb are the same. In any other case, you need to compare the Ka and the Kb of the conjugates. Okay, so that's our answer key for this problem. And let's say I always like to have in my videos exam tips. So let's think about a scenario where you're running out of time. There's like 1 minute left in your final exam and you didn't manage your time very well. And you need to submit your answer. And let's look at the question. So we have, what is the pH of 1 molar aqueous solution of sodium acetate? And you can notice that so far we haven't discussed about any numerical values. We're only doing like qualitative analysis, not quantitatively. That's going to be a topic for next video. So if you had to guess the answer for this problem, we have 1 out of 5, right? So that would be a 20% chance, which is not very good. You have 20% chance for every single question. So it's always good if you can make an educated guess or improve your chances of getting the question correct. That's what I'm going to try to do here, just by looking at what we discussed so far. So we have sodium acetate with NaCH3COO, and let's do exactly the same process we've done so far. we're going to break apart into its ions, so Na plus and CH3COO minus, and see what was the base and what was the acid that produced those cations and anions. So sodium plus comes from NaOH, which is a strong base, and CH3COO minus comes from CH3COOH, which is a weak acid. So just by comparing those, we see that we have a strong base and a weak acid, so the strong overcomes, which means that my pH should be basic. And if it is basic, it means that my pH should be greater than 7. So just by looking at those options, I already increase my probability of 20% to 50% by just eliminating options A, B, and C. Okay? All right, I'm glad we were able to make it this far. So let's just do a quick recap of what we discussed today. So salts are compounds made of cations and anions, and they are mostly commonly produced from what we call neutralization reactions, which simply are reactions between acids and bases. The cation of the salt comes from the base, while the anion comes from the acid. And in order to determine the pH range of a salt, what we need to do is do exactly what was done with the doodle example, where in order for us to determine the characteristics of the doodle, we had to look at the parents. The same thing needs to be done for a salt. If you want to understand the characteristic of a salt, one needs to look at the acid and the base that produced that salt. So in the examples we discussed today, we observed that if a salt is derived from both a strong acid and a strong base, the salt will be neutral because none of those can overcome each other, and their ions will be spectator. Just watch out for the sole exception that we discussed, which was in the case of polyprotic acids such as H2SO4. In that case, HSO4-, which is a conjugate base of H2SO4, can also behave as a weak acid, HSO4- and loses its extra H+, which makes it not a spectator ion and in fact a weak acid. Okay, so be mindful of that exception. In the case of a salt being derived from one strong and one weak species, the salt will be acidic if the anion comes from a strong acid, such as H4Br, or basic if the cation comes from a strong base, such as NH2CO3. Lastly, in the case of salts formed from both weak species, one needs to pay close attention to the Ka and the Kb of the weak acid and base. The larger value will determine the pH range. Congrats, you made it! So thank you for watching, and please subscribe to the channel if you think it was helpful. Please share with your friends, colleagues, and classmates if you think that could be helpful for them too. All right, don't forget, we can talk about any topic in chemistry. Bye-bye. See you in the next video.